Hey guys, I just wanted to make this video because to kind of correct a mistake I made earlier on. So I saw that and I kind of forgot that I made this mistake, but then someone reminded me, so I just wanted to correct myself. Okay, and so let me tell you the incorrect one that I stated in class. The wrong this is about if you have subgroups, the orders of the subgroups have no common factors, and the product of the suborders of the subgroups is the order of G. Okay, and then I wrongly stated that in this situation G is isomorphic to the direct product of H times K, and then the reason this came up was that in the coursework 2, someone used this to prove that a group of order 24 is solvable. Okay, and if this theorem were true, that would be a correct answer, so I didn't take off marks for that. But this theorem is like not true. So yeah, I just wanted to correct it. Okay, what is the right statement? All right, so what is an example which tells you that this is not true? Well, actually, just the reason that made me think of this is like look at of course, like what's a group of order 24? S4. Look at S4. Okay. So what does this tell you? Well, like in S4, a decomposition like this would tell you that a C-log 3 subgroup and a C-log 2 subgroup would both be normal. But the C-log 3 subgroups are definitely not normal. Okay, so it turns out this fact means that even though in S4 you have a group of order 8 and a group of order 3 satisfying all the conditions that I've written down here, it's not true that G is isomorphic to the direct product of the C-log 2 subgroup and the C-log 3 subgroup. Okay, for this reason. Okay, so let's try and correct ourselves. Well, we need to assume all the same assumptions, but we need to assume that both H and K are normal in G. Okay, so let's try and prove our corrected theorem. I guess just, for completeness sake, proof. Okay. Well, first of all, just look at the commutator subgroup of H and K. In other words, the subgroup generated by commutators of H and commutators of K, like, okay. And we claim that this is contained in both H and K, so in their intersection. Okay, so claim is that this is contained in H intersect K. Let's prove the claim. Proof of claim. Well, just take any element of, like any of these generators. Commutator of H and K is just HK, H inverse, K inverse. This is in K since K is normal. It's like H times something in K times H inverse, so it's in K. This is in K as well. So there's something in K times something in K, so this is in K. But it's also, you can also think of it as H times KH inverse K inverse. This is in H since H is normal. This is also in H. So this whole thing is in H. Okay, but it's the same thing. So it's in both H and K, so it's in their intersection. But now their intersection, the order of the intersection divides the order of H and also the order of K. So what does that mean? So what is by Lagrange's theorem, the order of H intersect K divides the order of H, and also the order, by Lagrange's theorem, the order of H intersect K divides the order of K. So it must divide also their GCD. In other words, it must divide 1. Well, a divisor of 1 has to be, like a positive number that divides 1 has to be equal to 1. Okay, so since their orders have no common factor, we have H intersect K has one element. In other words, it's trivial. Okay, well, that tells us, well, each of these commutators are in the intersection, so each of these commutators are trivial. That's for all H in H and K in K. In other words, every H commutes with every K. And this is what we need to show that we have a direct product. Okay. So let's define phi from H times K to G. And what does phi do? Well, it takes H comma K, in other words, something in the Cartesian product, and just multiplies them together. Okay. And now we have to ask ourselves, we have to ask ourselves, is this onto, is this one-to-one, is it a homomorphism? First, let's answer, is it a homomorphism? Phi is a homomorphism. Why? Well, if I look at, so multiplication in H cross K, it just works like this. We just multiply the H's and multiply the K's. Okay. Now phi of this is HK, and phi of this is H prime K prime, and phi of this, so we're asking, in order to be a homomorphism, we need this for this to be true. Okay, but this is true because K commutes with H prime, so we can switch them, and if you switch K and H prime, you get this. But K H prime equals H prime K. So in other words, 5HK times 5H prime K prime equals 5HH prime KK prime. Okay, so we have a homomorphism. What is the kernel of phi? The phi just takes a ordered pair H with K and multiplies them together. So suppose HK is in the kernel of phi. Well, that would mean that H times K is the identity. Because phi just takes this ordered pair and multiplies them. So if that is trivial, then that just means H times K is the identity. Now you can see that that means that H is K inverse. Now H is in H, K inverse is in K. So in other words, H is in H, but but also in K. So it's in H intersect K, which we've already seen is trivial. Okay. So H is trivial, K inverse is trivial, so H equals K equals the identity. Therefore, H comma K is just the identity of H cross K. Okay, so therefore phi is 1-to-1. And now, H times K, how many elements does that have? Well, it just has number of elements of H times number of elements of K elements. That's true for any Cartesian product, even if it's not a group. Okay, and we've assumed by hypothesis is the number of elements of G. So the image of phi also has to have the number of elements of G, since phi is 1-to-1, and that implies that that phi is onto. And so phi is 1-to-1 and onto, it's an isomorphism. And in other words, G is isomorphic to a direct product. And that leaves us now with a corrected statement. And it's okay if it doesn't bother you, but it did kind of bother me to leave that. Okay, thank you.